So for our next talk, we have Devora Chait-Roth, who's going to be presenting consistent updates for scalable microservices.
Okay. Hello, everyone. I'm Devora. I'm a PhD student at NYU. This is work that I did with Kedar from Nokia Bell Labs and my advisor, Thomas. And we're going to talk about consistent updates for scalable microservices. Now, this work is about live updates. So that's an update that you apply to a system while the system is still running. And when you do a live update, you can enter into a state that we call mixed mode, where you have an old version and a new version worker concurrently active. It's a mixture of the two. Now, when you have two versions active at the same time, that can lead to all sorts of errors. So what we do is we propose a way to guarantee that even when your system is in mixed mode, it still behaves consistently, meaning it still looks like it only has one active version, even though really it has two. OK, that's the first half of this title, but first let's talk about the setting of scalable microservices. We're going to use a basic messaging service as an example, like WhatsApp. In a microservice, you have a set of clients who send requests to workers, so like send a WhatsApp message. The servicing worker will operate on a shared data store, so put that WhatsApp message in the recipient's inbox, and then send some kind of response back to the client. Now, the full functionality of the service is contained in the workers. And at some point, you're going to want to update your functionality. Now, assuming that your new version is not buggy, we want to know, how do you update from the old version to the new one? OK, so a very easy way to do this is what we call an atomic update. You'll just shut your whole system down. You update all of your workers together atomically, and then you bring everyone back up. But if you have an online service that can't be shut down, then updates become not simple. And these are live updates. You're updating your system while it's still running. Now, how can you possibly do that? It sounds like changing the tire of a car while you're still driving. I do recommend this video. Now, now, how do people pull this off for live updates? Well, one way is you can use duplication. So you can just make a whole new set of workers that are updated. And then when that set is ready, you switch your traffic over. But this has the downside of you need to duplicate all of your workers. Instead, you could do something kind of simple called a rolling update. And you just go worker by worker, updating your workers, and whoever is not being updated is available. So why would you ever use extra resources to do like a duplication style update? Because while you're updating, you have a mix of versions active at the same time. We have old and new version workers, both servicing clients, both accessing the same data store. And this is what we call mixed mode. Your service is not the old version. It's not the new version. It's a mixture of the two. And that is very dangerous. Now, to demonstrate why, let's go back to our WhatsApp service. So let's say that we're updating WhatsApp so that it automatically translates a message to the recipient's native language. OK, so we have Bob in America and Claire in France. And Bob sends a message to Claire in English. And we're doing a rolling update. It's mixed mode. So his message gets routed to a new version worker. So as per the update, it will automatically translate that and puts the translated version in Claire's inbox. OK, now Claire reads that message. And she says, oh, it's an updated system. I'll send a message back to Bob in French, and the system will take care of that for me. But we're in mixed mode, and her message can be routed to a non-updated worker. It doesn't translate the message. And being American, Bob does not know what the message says. Now, this is a very lighthearted example, but it's had very, very real bad consequences. In 2012, a trading company called Knight Capital went bankrupt in mixed mode. A message meant for a new version worker went to an old version one, and that triggered an infinite cycle of trades, and that bankrupted the company. And the problem has not gone away. The AWS outage in October was a type of mixed mode. You had old and new DNS configurations that were active at the same time. And the Cloudflare outage in November took so long to fix because the system, it was a rolling update. It was in mixed mode. And their diagnosis software could not address the bug in mixed mode. In SOSP 2021, this study examined over 100 real-world update failures. And they found that 63% of these were caused by cross-version interactions, by this mixed mode state, and 2/3 of those were catastrophic. So this is a real problem. What has been done about it? There's work on resource duplication, but that's like just an expensive way of avoiding mixed mode. It's not addressing mixed mode. There's work on type safety and preserving invariants, but type safety does not protect you from mixed mode, and writing good invariants is hard and system-specific. And there's work on the setting of network updates, but it's a little bit too restricted to really address our problem because there's no data store, and the only updates that you can do are changes to path configurations. Really what we're missing is a generalized idea of update consistency and formal foundations for us to reason about mixed mode updates. But without this, we can't really prove anything at all. And this is where our contribution lies. We give the first formal reasoning framework for mixed mode updates, a definition of update consistency, an inductive proof method for update consistency, and algorithms for consistent mixed mode updates, which we prove consistent using our inductive proof method. Hooray. Now, everything that we did is built on our definition of update consistency. So before we get too formal and people start to space out, I want to give an intuition here. And for this, let's return to our problem. Now, what went wrong here? It's very, very tempting to say what went wrong is that we are in mixed mode, because we know that the system works well in the old version. And we know that the system works well just the new version. When we're in mixed mode, that's when things go wrong. And it's true, that's when things go wrong. But being in mixed mode isn't actually the problem. We want to be in mixed mode. We want to do these rolling updates. The problem is that our clients saw that the system was in mixed mode. They experienced the effects of mixed mode. But if clients don't see the mixture, if to them it just looks like the system updated atomically, then we know that the internal inconsistency has no effect. And this is our definition of update consistency. To every client, it looks like you did an atomic update. Because then we know that the behavior of the system is indistinguishable from this clean switch. You're not experiencing the effects of mixed mode. Now, I want to say this is a conservative definition, because there might be specific cases where clients can see that you're in mixed mode and nothing terrible happens. But we want a standard that's going to ensure that regardless of your system, regardless of your update, you don't experience mixed mode failures. And with this definition of update consistency, we can design consistent mixed mode update algorithms. And we use an update manager. It's sort of like a scheduler component that's going to intercept all of the requests coming in. It will inspect the properties of these requests, and it will very cleverly decide whether to send your request to a non-updated or an updated worker in such a way that it will ensure that no client sees the mixed mode behavior, that to every client it looks like an atomic update. And with our formal foundations, we developed a proof method for showing that our update algorithms are indeed consistent. Okay, now if you want to go to sleep, you can. We're going to make everything more formal. So first I want to talk about two important assumptions that we're making on our system. One is it's a black box to clients. They don't know the particular actions that the workers and the data store are taking. And similarly, clients are mutually independent. They don't know what requests and responses other clients are getting, right? All anyone sees is their own requests and responses. Now, we represent every single one of these processes as a transition system with FIFO channels between clients and workers and the data store. And the behavior of the system is traces over an alphabet of send and receive events. Now, in the paper, we really deal with computations. We're concerned with states also, but for the talk, we're just going to focus on actions. Now, workers are the only processes that are being updated here. But when workers communicate with clients and with the data store, that communication is going to be impacted by the version of the worker. So we mark all communication with updated workers as updated, and everything communicating with non-updated workers as non-updated. And now we can build a trace that is coded by version for every single action, for every single process's actions. Now, this is an atomic update because we can see that there's one point where the whole system switches over all at once atomically. Now, in contrast, this trace shows a mixed mode update. You have that mixture of versions active. And in order to show that a mixed mode update is consistent, there has to be an atomic update that is client equivalent to it, meaning equivalent in terms of client observations, because that's really what we care about. Even though the trace is recording the full message passing of the entire system, clients are seeing this very restricted view. So if we start with a mixed mode trace and we just project out the client observations, then there's like a whole world of other traces that are equivalent to that on the client observations. And if one of those has an atomic update, then we know that our mixed mode update is indistinguishable from an atomic one from the client's perspective. And this is our formal definition of update consistency. A trace row is update consistent if for every client C, so fix a client C, and there exists a trace with an atomic update that is C equivalent for that client to your original trace. And I want to emphasize here that this is a for all exists property. It's not exists for all. So this perceived atomic update point can differ from client to client. So Alice can say, oh, there's an atomic update at this point, and Bob could think that the system is still non-updated there, and he sees an atomic update later. All that matters is that every single client perceives an atomic update. Now, if we want to prove update consistency, how can we find an equivalent atomic trace? So one method that we use is commutativity. So let's say we have Alice sending Bob a message via an updated worker. So that gets stored in Bob's inbox. And then Bob sends a message to Claire with a non-updated worker, and that gets stored too. Now, from every client's perspective, this looks identical to if we switched the order of the non-updated and the updated actions. And this has an atomic update. So in other words, we're using commutativity to find equivalent atomic update traces. And this is the basis of our commutativity algorithm. Inputs which actions are commutative from their system. And the update manager is going to ensure that all of the requests are directed in such a way that if you ever have a non-updated action, it's left commutative. You could push it to the left of all the prior updated actions so that you have that atomic update. Now, all that really matters for our algorithms is the version of a worker. So we could just collapse everything here, just old or new. That's all that matters. And the first request, it doesn't matter where it goes because there's nothing to compare it against. But once that next request comes in during your rolling update, the update manager is going to inspect the semantic properties of that request. And it's going to ask itself, if this was sent to an old version worker, does it commute left? Now, if it does, that means that from the client's perspective, they'll perceive an atomic update. They'll see old and then new. And then it has the freedom to send it to an old version worker, or it could send it to a new version worker too. It has that ability, but now it could send it to either one. If the request is not commutative, then the clients will see, oh, this is not an atomic update. I see updated actions and then non-updated ones. So in that case, the update manager is forced to send it to a new version worker so that we make sure that clients don't see that internal inconsistency. Now, it might sound sort of obvious to use commutativity as a way to find these equivalent traces, but the proof that this algorithm is correct actually turns out to be sort of tricky. So let's talk for a second about how we reason about consistency of these algorithms. Now, what do we want to actually do? To prove correctness of an algorithm, we have to show that any trace that's produced by this algorithm has a client equivalent trace with an atomic update for every client. So first of all, for the purposes of our proofs, we switch our trace model. We've been talking in terms of interleavings, which are very nice and intuitive, but interleavings are a little bit too strict. They enforce an ordering on actions that are actually concurrent, that are not ordered. So for our proofs, we switch to a partial order model using Lamport happens before relation. So every process has a timeline that orders actions, and then actions are also ordered by sends and receives between different processes. And something that we're going to use for our proofs is called a consistent cut. Now, a consistent cut is a way to pinpoint a moment in time across distributed processes. So you collect actions from each process, and now if that is downwards closed, if the set that you have includes everything that happened before it, that's a way to express a point in time. So for example, if I want to pinpoint all of the non-updated actions, that last moment of non-updated, then I'll start here with C1's non-updated receive, and I'll work my way down the chain so that it's downwards closed. And here we go. This cut is a point in time. Now, if we have an atomic update in the partial order model, what that means is we should be able to create a consistent cut that has all of the old actions on one side and all of the new ones on the other. There should be a moment where everything switches. And this is not a consistent cut. We have updated actions in this moment in time, really concurrent with or before our non-updated actions. But if we look at this pair on the data store timeline, and we commute the old before the new, and now we build our cut again, those actions that were previously in the cut are now outside of the cut. And we have that atomic update, that clean divide between old actions and new ones. And this is what our commutativity algorithm is allowing us to do. It's guaranteeing that we can make these swaps until we get that clean divide. And a little more formally, we have an inductive proof method that's going to show that we can keep making these switches. Now, the proof method is really a classic ranking argument. So for that, we need a progress measure, or otherwise known as a ranking function, something to measure how close is a given trace to having an atomic update. And we build this progress measure so that an atomic update has measure 0. And now the argument, the proof method, is you have to show that you can keep making these, you can keep rewriting your trace in a way that's client equivalent, that makes progress, that decreases your progress measure. And once you show that, you'll be able to decrease until you get to this atomic update measure 0. Now, what is this progress measure? I'll talk for a second about that. Intuitively, you could try to count the number of blue actions inside the cut, right? You want that clean divide. The blue actions are out of place. But this is actually a little bit not sensitive enough. It really only cares about changes that happen at the border. So if we have this example, we have 3 blue actions outside the cut. And now we do the same thing that we did, right? We switch the old before the new. Intuitively, that should bring us a little bit closer. But that wasn't at the edge, so there are still 3 same actions inside the cut. So we wanted something a little different. So we can try to count the number of inversions. This is like a classic way to count, to measure sortedness. So how many pairs of new before old, how many things happen out of order. But this is also insufficient. And to show why, I'll give you a little glimpse of our other method for finding equivalent atomic traces, which is using backwards and forwards compatibility. Now, in brief, backwards compatibility is a way for a blue action to look red. For a new action, an action done by a new version worker, it looks like it was done by an old version worker. And forwards compatibility does the opposite. A red action can look blue. Something done by an old version worker looks like it was done by a new version one. And if we have a trace, so we really measure sortedness on the data store. I could talk about that offline. But if we have this data store timeline, and this action here is backwards compatible, so that means that it's equivalent to one where the blue action is red. And we count the number of inversions. So on the original timeline, we have this inversion over here that we don't have in the equivalent one, but we gained 2. And that shouldn't be happening either, right? Intuitively, this equivalent one is also closer to an atomic update. Now, very nicely, it turns out that if you take the ordered pair of the 2, the cut measure and the inversions, that works quite nicely. I invite you to see more details in the paper. But before I finish, I want to talk about our impossibility result. Now, in our algorithms, the update manager has to do this very important step. It has to look at the semantic properties of each request coming in. And that's sort of less than ideal, right? Examining requests takes work. We want an update manager that's oblivious to the requests coming in, that sends them, it chooses how to direct the requests regardless of what the particular requests are. Now, let's think about the properties that we're aiming for over here. We're aiming for an update algorithm that's oblivious, that directs things the same regardless of the semantics of the requests, that runs in mixed mode, and of course, that's update consistent. And if we think about the techniques that we've seen, a duplication update is oblivious. It does the same thing. You duplicate your workers no matter what your system is. And it's update consistent. It has that clean switch, but it's not in mixed mode. A rolling update is oblivious and it runs in mixed mode, but it's not update consistent. And our algorithms are update consistent and they run in mixed mode, but as we said, they're not oblivious. And we want to know, can we fill this middle section of this Venn diagram? And we show that that is impossible. You cannot have an update algorithm that simultaneously is oblivious, runs in mixed mode, and is update consistent. So in other words, we give semantics-based update algorithms for mixed mode, and that is the best that you can do. You can't have an oblivious algorithm here. Now, to sum up, we gave the first formal reasoning framework for mixed mode updates, a definition of update consistency, an inductive proof method for update consistency, and algorithms for consistent mixed mode updates. And I hope that I've inspired you to read the paper and learn more about this, because it's really just the beginning of our exploring this topic. We're thinking about, what if we're updating the data store? What if clients need to update? Or, how do you make this all more realistic? Usually it's not just one microservice. It's a whole network of microservices now. The microservices themselves are clients. And so there's really a lot to explore over here. And I invite you to read the paper, come talk to me. And thanks to these artists who provided all of these great graphics. Yeah, thank you very much.
Great. Looks like we have a question over here.
Hello, thank you for the talk. My question is about availability, where it seemed that perhaps one of the reasons for having multiple workers is that you can query them in parallel, and well, if one fails, you can still communicate with the others. But now you're putting something which mediates the interaction with the workers. So now, how do you have availability? That's the question.
OK, so usually when you have like a microservice structure like this, there is like a load balancer component. There usually is something in between the clients and the workers, but that is much less intrusive than the update manager. So you're asking a fair question, like how much does the update manager slow things down, right? And we're hoping to implement, this is like some of our next steps, is sort of how do you implement this system and get like some time bounds on how bad the update manager is. Yeah.
So perhaps a different, similar question is, do you have replicas, or do you replicate the algorithm manager, the update manager?
So that is a way to do it, but then you're going to have to, OK, so the bad part about this update algorithm that I sort of slid right past is that you need to have ordering requirements. You need to, if you want commutativity, you need to know what came before. And you don't exactly know that at the point that the requests are coming into the update manager because the workers are all operating in parallel. So we have to impose some kinds of ordering constraints. And that would get a little bit tricky with multiple update managers, and we need some kind of, I guess, a consensus program, something to deal with that. But would love to talk about that more because that's something that we're exploring. Yeah.
So thanks for the super clear and interesting talk. I have a definitional question. So the definition of update consistency that you gave universally quantifies over the view of every individual client. And one could imagine other definitions too, where you think about groups of clients. I'm curious if you guys have thought about why your choice is the right one, or what the trade-offs associated with that choice are.
Yeah. So what we gain from each client being individual, well, let me say it a little differently. Once you have groups of clients, you can sort of change your setting to be, instead of the clients being sequential, meaning in our model, each client sends a request and waits for a response. If you have groups of clients that are sort of, let's say, communicating with each other, so now they're sharing that knowledge. Now you could model that as just a single client sending concurrent requests, right? Like they send a request and get response back. And we actually started with that, but found this to be a simpler setting to build the foundations. But the individual ones really amounts to like this separation of knowledge between each individual client. Yeah.
OK, great. We can take one more, but in the meantime, can we have the last speaker come set up?
With your definition of input consistency, I feel like the old workers could get overworked pretty easily. Do you have an intuition, maybe even a formal proof, or something that they're not too overworked? OK,
so that's a really good question. Something that we're playing with right now is sort of you can You can look at the properties of your system. With our other algorithms, there could be an overworking on the updated workers. So depending on the properties of your system, like how many requests are commutative, you can be clever about the pattern that you use to update your workers. So if a lot of things are not commutative, and now let's say your updated workers are going to be working a lot, so you're going to want to make sure that when you start that update, you have a nice amount of updated workers. But you definitely playing with the way that you update the workers is going to be important in efficiency. Yeah, thanks.
Okay, let's thank Devora one more time.